Hello everyone, my name is Dr. KCH Apparao, working as an Associate Professor in Mechanical Engineering Department. Okay, in previous class we discussed the different laws which are used to find the rate of heat transfer through radiation process. Okay, so laws of radiation we discussed in previous class. In this class we will see different numericals which are based upon those laws. Okay, the first one we'll see the effective temperature of your body having an area. So area of the body has been given 0.12 meter square. And the temperature also given, that is the absolute temperature is equal to 527 degrees Celsius. Okay. So we have to calculate the following. First one, the total rate of energy emission. So total rate of energy emission, emitting energy. Next, intensity of normal radiation, we have to find out intensity. So next, wavelength of maximum monochromatic emissive power also we have to find out. So wavelength of maximum, so maximum wavelength del max we have to find out. Okay. So okay, so in this numerical, area has been given. Area is equal to 0.12 meter square. Then temperature 527 degrees Celsius. It should be converted into Kelvin. 527 plus 273. So that is 800 Kelvin. So first of all, we'll see effect. What is the first one? The total rate of energy emission. Means total rate of energy emission, emitting energy, total emitting energy. So for this one, you know that for finding the total emission energy, you know that law, that is the Stephen-Boltzmann law. So by using this law, you can calculate this one. Then EV, you know this formula because we already discussed in previous class. So sigma A T to the power of 4. You know this one, sigma, the value of sigma, Stephen-Boltzmann constant, 5.67 into 10 to the power of minus 8 into area. We have to construct this one. This is a 0.12 area into temperature. So 800 Kelvin to the power of 4. Okay. So if you solve this one, you will get this answer. That is nothing but 2786.9 watts. Okay. So next we will see the intensity of normal radiation. Okay. So this is the formula for the intensity of normal radiation. So that is nothing but okay. So intensity IBN is equal to total emissive power upon pi. So this is the formula. Okay. So total emissive power is nothing but 2786.9. Then the pi. So this is the value you will get. Okay. It means otherwise you can take like this one. Emissive power, that is emissive power is equal to sigma T to the power of 4 by pi. Okay. So 5.67 into 800 by, so 100 means 10 to the power of 8 means you can rewrite like this one. Okay. So by 100 to the power of 4. If you solve this one, you will get this answer. Okay. So this is the intensity of normal radiation. Next we will see the maximum wavelength where we'll get that highest emission power. Okay. So to find out the maximum wavelength, you know that the law, the Wien's displacement law, by using this one you can find out the maximum wavelength. You know this formula according to Wien's law, del max or temperature is equal to or sigma max lambda max So lambda max is it shows the maximum wavelength is equal to T upon absolute temperature by the constant. So 2898. Okay. So then T is nothing but 2898 by temperature T. Okay. This one is the formula. So by using this formula, you can find out the lambda max. Then my lambda max is equal to 2898 by temperature. Temperature is nothing but 800. So okay, if you solve this one, you will get this one. So that is nothing but 3.622 microns. Okay. So this is the lambda max, where you will get the maximum monochromatic emissive power. Okay. So in this way, just you can solve the different numericals also. Next one, we'll see a black body. Temperature of that black body is 300 Kelvin. This emits radiation. So you have to calculate the following. The first one, monochromatic emissive power at a particular wavelength. So lambda max, otherwise lambda is equal to 7 mu m. Okay. So you have to find out the monochromatic emissive power, EB. Lambda. EB lambda. EB shows the total emissive power. EB lambda shows the monochromatic emissive power. Next, wavelength at which emission is maximum. So emission is maximum means that shows that by using the Wein's law, we can find out that one. So that lambda max is equal to into T is equal to 28. That is the 98. Okay, so this is the formula. So lambda max is equal to 2898 by temperature. So by using this formula, you can find out the wavelength at which emission is maximum. It means lambda max. Next, maximum emissive power. Maximum emissive power can be obtained by the help of the Stephen-Boltzmann law. EB is equal to, you know this one, sigma, if area is there, T to the power of 4. Okay. So next, total emissive power. No, this is the total emissive power. This is the total emissive power. Okay. So maximum emissive power. So it means EB lambda at Y max, lambda max. So at particular wavelength, we'll get the maximum wavelength. So it means by using this lambda max, you can find out. So we'll say first of all, first one is the monochromatic emissive power. How to find out the monochromatic emissive power, particularly at wavelength lambda is equal to 7 mu m. Okay, 7 mu m. So you know this is the formula for this one. The formula is C1 into lambda to the power of minus 5 by C2 by lambda t. Okay, so to the power e to the power of this one minus 1. So this is the formula by Planck's distribution law. So by using this law, you can find out the monochromatic emissive power at a particular wavelength. This lambda is equal to 7 mu m. Okay. So C1, you know that was we know this one from the data book. We can take this constant also. C1 is equal to 0.374 into 10 to the power of minus 8 watt meter square. And C2, another constant, that is a 14.4 into 10 to the power of minus 3 meter Kelvin. Lambda is equal to, so 1 into 10 to the power of minus 6. So for this lambda. Okay. So if you substitute these values here, just you have to substitute the value of t. Okay. Remaining all constant you can take from the data book. Then EB lambda is equal to, okay, the first one C1 into lambda to the power of minus 5. Okay, you know this lambda by lambda into uh, 3000 minus 1. So it is the exponential of this one minus 1. So then the value is equal to, you will get 3.10 into 10 to the power of 12 watts per meter square. So this is the monochromatic emissive power energy. Now we'll see the maximum wavelength, how to find out the maximum wavelength. Okay, so this is the maximum wavelength. For this one, you know that from the Wayne's law. So maximum wavelength is equal to lambda max into T is equal to 2.9 or 2898 you can take, or 2.9 also you can take. Okay, so 2.9 into 10 to the power of minus. So then lambda max is equal to 2.9 into 10 to the power of minus 3000. If you substitute these values, you will get the lambda max. Lambda max is equal to 0.966. Okay. So at this particular wavelength, you can find out the maximum emissive power. Maximum emissive power. So that is the formula is equal to EB lambda max. EB lambda max is equal to 1.307 into 10 to the power of minus 5 T to the power of 5. So these formulas we already derived in previous class also. You can take this. Okay. Here if you substitute the value of T, then you will get the value. So this is the maximum emissive power. You can take this one. Now we'll see. So how to find out the total emissive power by using Stephen Boltzmann law. Total emissive power is equal to, if the area is not mentioned, means sigma T to the power of 4. You know that 5.67 into 10.67 into 10 to the power of minus 8 into T is a 3000 to the power of 4. And write like this one also, 5.67 into 3000 by 100 to the power of 4. Okay. So if you solve this one, you will get the EB. EB lambda is the monochromatic emissive power. EB is the total emissive power. Okay. So how to find out? You can find out by using this formulas. Now, so this one already solved this. So one more numerical is also there here. We can see that one also. A black body emits 200 Kelvin. So first we have to find out the monochromatic emissive power at 1 V lambda, EV lambda. We have to find out that mu is equal to, that lambda is equal to 1. Okay, 1 microns you can take. Next, wavelength at which emission is maintained, and next to lambda max also you can find out. Lambda max into T is equal to 2898. Okay, so this is the formula. By using this one, you can find out the lambda max 2898 by T. T is the 2000 Kelvin, not 200, 2000 Kelvin. So similar numerical like the previous also 3000 Kelvin we solved that one. Next, maximum emissive power or total emissive power also we can find out. So the same numerical is similar to this one. You can see here, very similar to this numerical. The first one also the monochromatic emissive power at 1 micron, that numerical. Next, wavelength at maximum emission is, so you know that formulas. Next, maximum emissive power by using these formulas, EB lambda, and next one is the lambda max T. So by using these formulas, you can find out that numerical. Okay. So these are the numericals which are based upon the laws of radiation. Okay. So there are 4 main laws: Planck's law. The first one is okay. So next Wien's law, Planck's law. Next one is the Stephen Boltzmann law. Is very important. Last one. So that is the Kirchhoff's laws. Also you will see. So in Kirchhoff law, emissivity is equal to absorptivity. We'll see in next class also. Thank you. So these are the textbooks for the reference I have given. You can refer these textbooks to solve more numbers, number of formulas, number of numericals which are based on the laws of radiation. Thank you for listening this class.
Like, share and subscribe. Hit the bell icon for more updates.